Find the minimum value of z. In this problem, the objective function to be minimized is z equals 4 times x1 plus x2 plus x3. The constraint set is composed of two equality constraints where decision variables x1, x2, and x3 are non-negative. Due to the equality constraints, an initial feasible solution is not obvious. To resolve this issue, we'll divide the problem into two separate phases. The purpose of phase 1 is to determine an initial feasible solution by introducing one artificial variable for every equality constraint, setting the value equal to the right-hand side, and solving a separate linear programming problem purposed to minimize the sum of the artificial variables. Once the sum of the artificial variables equals 0, an initial feasible solution has been found, and the artificial variables can be removed from the constraint set. Then, we can move on to phase 2 and solve the original problem by the simplex algorithm using the initial feasible solution found in phase 1. Setting up the tableau, we have a row for the phase 1 cost coefficients and a second row for the phase 2 cost coefficients. Our objective for phase 1 is to remove all artificial variables from the basis, so the value of z1 equals 0 when the tableau is in canonical form. To put the tableau in canonical form, we must perform a pivot operation on the non-zero entries in the identity matrix. Therefore, we subtract 1 times row v1 and subtract 1 times row v2 from row z1, and the simplex tableau is now in canonical form. Next, we begin the algorithm by pricing out. x1 has the smallest negative reduced cost coefficient of -5, so x1 will enter the basis. Next, the ratio test is performed, and since 1 is a smaller positive number than 2, artificial variable v2 will exit the basis. Lastly, we need to perform a pivot operation for the tableau to be in canonical form. To do so, we'll add 5/3 of row x1 to row z1, subtract 4/3 of row x1 from row z2, subtract 2/3 of row x1 from row v1, and divide row x1 by 3. So after pivoting, the tableau is in canonical form, and artificial variable v2 is non-basic and equals 0. However, artificial variable v1 is still basic and equals 2, so we have not yet found an initial feasible solution. We return to pricing out, and notice -3/4 is the smallest negative cost coefficient, which is associated with variable x3. Therefore, x3 will be the next variable to enter the basis. From the ratio test, we notice that 3/2 is a smaller positive number than 3, and therefore, artificial variable v1 will exit the basis. Next, we'll perform a pivot operation to convert the tableau into canonical form. This time, pivoting involves adding 1 times row x3 to row z1, adding 1/4 of row x3 to z2, subtracting 1/4 of row x3 from row x1, and multiplying row x3 by 3/4. Since both artificial variables are now non-basic, their values are 0 and phase 1 is complete. Now, row Z1 and columns B1 and B2 can be removed from the tableau. Now we begin phase 2, and we begin with an initial feasible solution of x1 equals 1/2, x2 equals 0, and x3 equals 3/2. From pricing out, x2 will enter the basis and replace x1 because row I of x1 has the smallest positive ratio bi over ait. We perform one last pivot operation and arrive at a unique optimal solution since the reduced cost coefficients of all non-basic variables are positive. The optimal x vector is 0, 2/5, 9/5. When plugged into the objective function, the optimal objective function value equals 11/5. When reviewing the possible solutions, the answer is C.